I'm going to show my solution to the Paul McWhorter's picoW class lesson 90 homework assignment, which was to produce a count up timer that runs slowly. On the left you can see my built breadboard, and on the right you can see my program written in Python. Starts off showing the picoW program, but let's first look at how the picoW program gets activated. It's down at the bottom. And here's how that happens. The program writes out a test started message, takes the timestamp so it can compute how long it runs, activates the picoW program, sleeps. Note that for the values I have there, it'll end up sleeping for 10 seconds. When it wakes up, it deactivates the picoW program, thus breaking it out of its infinite loop, and writes an ended message about how long it ran, which should be 10 seconds. Now let's go look at the picoW program and see how it works. It's the same as what Paul did for the countdown timer, with one important change, well, two actually, the delay. Instead of counting down, it inverts the number that's in the X register, which will change ones to zeros and zeros to ones, or does the same thing as replacing it of using the value in the X register subtracted from 15. So it'll go from 0 up to 15 out to the LEDs. This IRQ instruction, I'll explain in just a second, but it's used to get a timestamp that we can use to compute how long it actually took between moving values into the LEDs. Now the delay that was added is right here. Whatever's in the ISR register is used as a delay count. We have to see how that's computed. We'll do that shortly. And this instruction just jumps to itself that many times. So this will add a whole bunch of instructions inside of this display big main loop up here. When the delay count is reached, we branch back up to the display loop, where the next value will be written out. So this will decrement X, come up here, and then again hit that IRQ instruction. So let's first see how the delay count is computed, and that's done here. The Y register is set to 0 and moved into the ISR register, and the Y register is set to all ones. The ISR register finally is set to 10 ones in its low order bits, which is the same as setting it to 2 to the 10th minus 1. That number 10 was arbitrarily picked to put into the Y register here, but it can be any value between 1 and 32. So before we run it, let's look at how this IRQ is used. We have to look down a little further here, and we see there's one additional instruction in the Python program to set something. Every time the IRQ instruction is executed, this will run a timestamp print, and we can use that later when we see the delay. So let's look back up at the top and run it. Right now we're set at 10 in Y, and we're going to run for 10 seconds. So let's run it. Watch the LEDs. They're counting up from 1 to 14, 15, and then back down, and it counts up to 3. And that timer down in the main Python program, that sleep wakes up and stops the program. So we were at 2 to the 10th minus 1. Let's take a look at what these timestamps are. Here's where they were written out. This is the time for when 0 was written out. This is the timestamp when 1 was written out, and so on. The difference in this would be how long it took to write the 1 value. I have from a previous run the values, so time for 0, time for 1, and so on. I wrote a statistics program in Python that converts those values, the consecutive values, it calculates the differences. So we can see when we wrote 1, it took roughly half a second. Now, further down, when I used that value for the ISR register of 2 to the 12th minus 1, it took 2.04 seconds to write 1. Now that's an agreement. The value for 2 to the 10th minus 1 was roughly half a second. The value for 2 to the 12th minus 1 should be approximately 2 to the 2 times the value for 2 to the 10th minus 1. So 4 times this value, and it is. I'm not going to run these other tests, but at 16, that's 2 to the 6th times the 2 to the 10th value. 2 to the 6th is 64, times 0.5 is 32, so that's in agreement. I also ran this with a frequency of 10 million and ran a few tests, which I'll show you the results. Not going to run it now. The summary value here shows for the frequency of 2000, here was our half a second, here was our 2 seconds for 2 to the 12th, and our 32.7 seconds for 2 to the 16th minus 1. I didn't run the 2 to the 32 minus 1 test, and here's why. That would have taken this long. No way we're going to run that. And finally, here are the values for using 10 million. But 2 to the 10th minus 1 didn't even take a millisecond. And the 2 to the 32, we could actually run it, took 429.5 seconds. All in all, this was a fun program to write. Hope you enjoyed it. Thanks for your time.